Hello. So I think we can start now. Can everybody hear me? Please say it via the chat, so I'm sure that everybody can hear me. Yes, okay. Then we will start. Thank you. Today it's the class. Today it's a class about gas turbines and performance. I will just show the schedule of today. And so this is the schedule of the common classes. So last Friday we had the gas turbine overview class. Today it's about gas turbines and performance and application. The next two lessons, so both from coming Friday and next Tuesday, will be given by Vera Popovic on material mechanical aspects. And next Friday, the last day before Christmas, I will do something about combustion. And then we'll continue after Christmas with controls. So that's all about it. I had a request from maritime technique students. So they apparently have another exam, part of them, at the same Monday. So if more students have that problem, please let me know, then we can discuss how to solve that. I'm also discussing if there's some, you can either do the resit or we also look for an alternative solution, depending on how many students there are. So please let me know if there are more maritime students, or maybe maritime students in between each other, please check how many people have that same exam at the same date on Monday, January 25th. So what are we going to do today? So today we're going to combine the previous classes on gas turbine performance, and we will study the impact of different parameters that affect the performance. So the overall thermodynamics, we will also apply the turbomachinery performance and diagrams. So 2 classes ago, we derived the compressor chart and the turbine chart, and today we're going to do that. And also by what the performance is limited turbine materials. So actually important for this is that you will be capable to do simple or quite simple performance calculations. We'll do calculation today, but at least one of your exam questions will be a similar question. I would like you to understand and to apply the main parameters that affect the performance. And I also like you to understand the difference between a single shaft and twin shaft engine. So today we have quite a broad discussion. First of all, before we start all these interesting stuff, I will discuss briefly about the homework assignment. I will put this. I put this on the website. So I will wait a minute. I will share where you can find homework assignment. This one. Yeah. I hope it works. We can enter it. Sorry about that. Then I have to do Google there. Okay. So we're at the bright space. So we look at content. We have the assignment, performance and combustion. And then we have the homework assigned mechanical. So please, in a group of 2 persons, you can hand it in by January 8th, or the TDL student via the standard brightspace solution, non-TDL, please email to me. And actually, this homework assignment is of two parts. So first of all, you have to design your own gas turbine cycle. And actually, that's more or less the same situation we do today. And the other one is to use a Thermoflow software. So we have a free trial license for the Thermoflex Lite package, and you can do that. So then this is about the student. So this is about the question I would like to ask you. So please do them in two of them. I will check them on plagiarity. So don't copy from your fellow students. I really want you to understand it. So if we go one back, wait a minute. Content. So if you look here, we included it. Tools for assignment, assignment 3. Forms and calculation. So we have the Thermoflow 23 free trial setup. So you can download this zip file, you have to decompress it, and you can install that on your computer. And there is a brief explanation also included here with how to do it with Thermoflow, how you can use it. So just short explanation about Thermoflex and how to do it. The idea is really that you make a small gas turbine cycle. There's one gas turbine freely available in the model you can play with, so you can use that in your system, and you make them a simple model of that. For the non-TU Delft students, wait a minute, we do it on Drive. There it is. There it is. And then you have homework assignment 3. You have the same term for free trial setup. This is all there included here also. Okay, so this is about the homework assignment. I will go back to this screen, PowerPoint. Yeah. So all the information is on this locations. So, well, let's set it to January 5th. Well, and the work is January 8th. So please hand it in by January 8th. Group of 2 students, include your student number, and do things like that. Are there any questions now about the homework assignments? For the TU Delft students, only one student has to upload it. The lecture, it's 5 January. Well, negotiation, we do it January 8th. And Thermoflex, I showed you just where it is. So Toma, did you see where I did include Thermoflex, or do you still have a question about that? No question for the homework assignment? So you only have to, one TU Delft student has to submit. January 8th is the new deadline, and Thermoflex, I showed you where it is. Thermoflex, yeah. Okay, let's continue to the next slide. Okay, what are we going to discuss today? So we will start with a review of the previous lectures we'll do the first time. Then after that, we will discuss well, the dimensions parameters, compression and turbo diagram, and then we do some performance calculations. We start with a single shaft gas turbine. We show a little bit for the multi-shaft gas turbine, but that is, well, we don't do in detail because actually that's too complex to do it by hand. You can maybe do part of it, but the full multi-shaft gas turbine is not, it's possible, but not easy to do. Then we think about when do you apply what kind of gas turbine. So both for single shaft and multi-shaft, and we discuss the aero engines. And at the end, we will briefly show a little bit about dimensions of gas turbines and for what applications you should take care of different dimensions. So there we go. Wait a minute, I do it a little bit different. Okay. So the recalc of thermodynamic cycles I like to show you. And like I said, we always start with a medium at a low pressure, low temperature. So it's the begin state of medium. Then normally you have to compress it to a high pressure. So in a gas turbine, you do it with a compressor. Then you have to have heat. So in a gas turbine, we normally do it with combustion, but actually the main role of combustion in a gas turbine is just to deliver heat. And after the combustion and the compressor, we have, well, after compressor, we have a high pressure, and after combustion, we also have a high temperature. Then after those things, we go to the expansion. So in a gas turbine, we do it by turbine. And in expansion, we get work out of it. So part of the work is used to drive the compressor. And then we have some work left, hopefully, that we can use for useful applications. And like I said before, you always get to kind of heat out. That's really the consequence of the thermodynamic cycles. You cannot convert all incoming heat into power. You always have heat flow out, depending on the temperature levels. And then theoretically you have to cool it down, but you can also suck in fresh air. So this is really the cycle we go to discuss. And the most thing is compression, heating, and expansion. Well, we saw this for the gas turbine, looks similar like this. So the compressor in the gas turbine, there we have more or less isentropic compression. So if we look at the TS diagram, we go from 1 to 2 with isentropic compression. Then you have isobaric combustion from 2 to 3. So you add heat. Then the limit is normally limited by the turbine inlet temperature, so T3. And it's normally limited by the materials and the cooling. We saw that last time. So that's really a very important part in the development and the efficiency of your gas turbine. Then you expand it between 3 and 4. So you do it in the turbine. And then you have hot gases still available at 4. So this is really the cycle we have to do here. And the power that we can deliver is the power net gross delivered by the turbine is 3 minus 4, and the power consumed by the compressor is 2 minus 1. So these are the basic of simple diagrams. Now then we have the idle cycle versus a real cycle. So actually that's what we see here. And actually if the idle cycle, you have isentropic compression and isentropic expansion. And you have isobaric combustion or heat addition. So that is here. In reality, and for me it is very important that you get this right, is really, oh sorry, that you really, if you look like this, so we have here, oh sorry, so we have here TS diagrams, and we have all these lines you saw here. So the isobars, something like this. Then we always have the isentropic compression, like here, isentropic. So that is where you have a constant S. So delta S is 0. That's isentropic. And that's the ideal case. And the ideal case is that you can also let it expand like the same line. So it's reversible. It's the isentropic. But in reality, we don't have isentropic. We have all kinds of losses due to friction, all kind of stuff. And there you get something like this. And important to know is, like I said, this is delta T isentropic, is more or less delta H isentropic, if you have a constant Cp. And you see here delta T real. And for a compressor, it's important to know that the real work required to compress a fluid is higher than the isentropic. If you go to the turbine, so if you have a combustor, and then we go to the turbine, we can have the isentropic turbine, and then we have the real point. And for the turbine, so for the compressor, it's important delta T real is larger than delta T isentropic. But in the turbine, it's the other way around, because you get losses, so you can't get all the potential work out of the turbine. So there is delta T isentropic is larger than delta T real. And there you get this is the work, delta T real. This was delta T isentropic. What is important to know? And then, of course, these are the first things. So you have the non-idle case of the compressor, the turbine is the most important one. And in reality, you also have the non-idle case of the combustor. So you normally go a little bit away from this isobar. So this is really the discussion between isotropic and non-isotropic. And also, if you look at the efficiencies for the turbine and compressor, they're differently defined. We come back to that later. So we see here the difference between real delta A compression and delta A turbine. That's important to know here. Well, in most cases, we make our life a little bit simple, and there, so we have some idle cycle assumptions. So first of all, we assume constantly have a constant CP, specific heat, at constant pressure and volume, and constant composition. So that makes it possible that you can directly translate the entropy difference into temperature difference all the way around. For simple case, you can also assume the mass flow to be more or less constant. Because the mass flow added in the combustor, so that the main mass flow is really the mass flow of the air to the gas turbine. The mass flow in the combustor is only 1 to 3% of the total mass flow. So the first approximation you can assume to be the mass flow to be constant. Well, first instance we assume isotropic expansion. Later on we can have some isotropic efficiency included. We can include pressure loss or don't include pressure losses. If you had a heat exchange efficiency, in the ideal case 100%, and in all cases at the moment, in all these situations, we look at the total pressure, so including the kinetic energy. So we assume at this moment that when we're at the station where we evaluate the pressure, that the velocity is 0, so we can assume the kinetic energy to be 0 or included in the total pressure. So that's also how we the total static isotropic we define, and there we include the also the velocity, so the kinetic energy, to make life a little bit easier. And then this is something I like to discuss with you. So like I said, the efficiency, we have two types of efficiency, the isotropic and the polytropic efficiency. We will first discuss the isotropic efficiency. The next slide, I will also discuss the polytropic efficiency. But if you look at the isentropic efficiency, that is defined as the isentropic entropy difference divided by the real entropy difference. Like I said, in a compressor, the real is higher because you need more power in reality than the isentropic case to compress the air, because you have some losses. Well, we assume in this case that the CP is constant, so the delta H can be replaced by the difference in the temperature. So the difference in the temperature is the 2T isotropic means T1, or divided by 1. Well, for the T2 isotropic, we know the famous relationship, so the adiabatic compression relationship. And if you work it out, you can see, actually, this is normally, if you work it out, normally you're interested in the exit temperature of the compressor, so the real temperature, exit temperature of the compressor. So that can be calculated if you reshape this a little bit, like T1 plus this situation. If you do the same for the turbine, you have to be aware that's all switched around, because actually the only reason is that the people want to keep the efficiency below 1. So there in the turbine, the real work delivered, or the real entropy difference, is smaller than the isentropic entropy difference. So if you work that out again, the real, and we assume a constant CP also in the turbine, you can work this out in this situation, and then you come to this formula for the turbine efficiency, for the turbine outlet temperature of the turbine. And you see actually, so the real turbine outlet temperature is higher than the isentropic turbine thing. So this is all for isentropic efficiency. In parallel, you also have another definition, and it is polytropic. And actually, polytropic efficiency is more or less the adiabatic relationship, but a kind of efficiency is introduced in the coefficient. So for the compressor, it's 1 divided by the compressor efficiency. And for the turbine, it's the turbine efficiency, the polytropic turbine efficiency. So in general, you can either both polytropic and isentropic efficiency. Most cases, if you look at for as compressor as a total system, you normally use the isentropic efficiency. And you have, if you want to study a compressor that's built up of different stages, you can define the polytropic efficiency for all stages, and you can easily combine it because you can see that you can multiply it with each other. So you don't, if you have the same polytropic efficiency for one stage, you can multiply different stages with each other. So that's the advantage of a polytropic efficiency. They mix together. In our in our task we do, it's mostly we work with the isotropic efficiency, but in some cases also the polytropic is used. This advantage. So both can be used, but we normally use the isotropic one. Like I said, the pressure drop in the combustion chamber. So in the idle case, you have no pressure drop, and in the non-idle case, you have a kind of pressure difference. Actually, normally it's expressed in the pressure ratio of the combustion, or the amount of percentage pressure loss in the combustor. So the percentage loss versus the incoming pressure, and you can also express that in a pressure ratio. And then, of course, you have the efficiency of the combustor. So this is the enthalpy balance over the combustor divided by the incoming low calorific heating value of the fuel. So normally it's very close to 100%. Otherwise, it's not the good combustor, of course, but normally then you can assume the efficiency. If nothing is mentioned, you can assume that the combustion efficiency is 100%. So these are also non-idle situations for the combustor. Well, if you look like that, so if you want to study systems, and like we have a system built of normally have a compressor, a combustor, and a turbine, you normally actually want these things to know. So the enthalpy difference, the efficiency, and the power. You can express them as a parameter of a number of parameters. So, for example, the flow parameters, so the viscosity of the flow, the RPMs, the dimensions, the mass flow, the density, the speed of sound, and the specific heat ratio. So you can question that, and if you work that a little bit out, and you work it out from mathematics, you can show actually that all these parameters, and that's important, can all be expressed as function of those 4 parameters. And if you assume a constant, so it's some kind of dimensionless mass flow, dimensionless rotational speed, the Reynolds number, and the ratio of the specific heats. And well, normally the Reynolds number is normally quite large for turbomachinery. So if you assume a large enough Reynolds number, then it's all turbulent and in the same flow regime. So the Reynolds number dependency will be very weak. So you can strip this out. And also, if you have more or less a constant or more close to ideal gas, you can also assume gamma to be more or less constant. And in that way, you can express that all, actually for those situations, all situations can be expressed as 2 parameters. And normally these 2 parameters are chosen for turbomachinery. So that is the dimensionless mass flow, made dimensionless by the square root of temperature and the pressure, and dimensionless rotational speed. Like I derived, I think 2 classes ago, this is more or less based also on the dimensionless Mach number. So the dimensionless Mach number of the dimensionless Mach number of the inlet flow, and this is dimensionless. This is the rotation speed versus speed of sound. So it's rotational Mach number. So for this, and if you really look at the high efficiency equipment used in industry, this all plays in a kind of inlet Mach number and rotational Mach number. And they normally call it the reduced mass flow rate and reduced speed. So these things, these 2 parameters are normally used to make your inlet parameters non-dimensional and to be able to scale to each other. And that way you can apply it to all the temperatures. For instance, you can also apply it to all the fluids, but it would be easy to do that like that. Okay, there's a question. The air combustion includes both combustion. There's a question. The efficiency of the combustor includes both combustion loss and heat losses. Yes, that's right. If you have external heat loss to the outer world, if it stays in the system, they're included in total heat balance. But actually, like I saw in the first picture, The only role of combustion, you have to make it simple model like we do. The only role of combustion is to add heat. And if there less heat is added, either because you have incomplete combustion or due to heat losses to the environment, yeah, that makes the cycle less efficient. So you should include them both in the efficiency of the combustor. Yeah, that's a question from the chat. Okay, so we talk about reduced mass flow and reduced speed, and we saw those paragraphs, those diagrams some times ago. So if you look like a compressor diagram, on the x-axis you have the reduced mass flow, and on the you have here the lines of this constant speed, dimensionless speed. Yeah. 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 So here's the dimension of less of constant speed, and this is the normal operating line where you're running a gas turbine, especially a multi-shaft gas turbine. You try to operate it here at a certain distance from the surge line. So it's the surge line, all kinds of stuff here, and this is really important. Yeah. And we discussed this last time. You have the different types in the compressor diagram, where you can have here those lines of constant speed, and then you see here's the dimension mass flow, and here's the pressure ratio. Important to know, and it's also very important to know for an axial compressor. If you really like here, this one. What's very interesting here is that these lines, well, more or less are vertical. So you have a constant mass flow rate, constant dimensions of mass flow rate, or reduced mass flow rate at the same pressure rate, so that the pressure ratio does not determine the mass flow rate anymore. You see here at the low pressure rate it still determines, but at this one it won't determine it. And this is sometimes called in compressor theory the stone wall, because you don't get any flow anymore through it. Also because in this situation you just follow this mass flow. You will see when you have the thermoflex example, you will see actually they simplified also the compressor curve like this, with this kind of stone wall where you have a constant mass flow at different pressure ratios. So this is a typical compressor diagram with the different lines in there. And like I said, there are a number of parameters affecting the performance. So first of all, you have the inlet pressure drop with compressor performance, like I said, is mainly the isotropic efficiency, compressor pressure drop, and the compressor efficiency. So the heat loss, either incomplete combustion or heat loss to the environment. Like I said, very important is the turbine inlet temperature, the turbine performance, outlet pressure drop, and then you have, of course, the pressure ratio, things like also design parameters. And parallel to that, also the ambient condition, fouling, internal leakage, diagodynamic shape degradation. Well, I can sum, I think, 10, 20 other issues here, but a lot of those things all come together to your performance. We make it a little bit simple in this class, but in reality, you have to take this all into account into your performance calculations. So when we go into the performance calculations, so we will now discuss a single shaft gas turbine. And I'll do some calculations for that, yeah. So we have just atmospheric conditions, so 15 C, so 288 K and 1 atmosphere. And what we want to do is the TO2 and the net power efficiency for different pressure ratio. And we can consume constant mass flow, so we can neglect the fuel mass flow, constant CP, and no pressure loss, and we assume mechanical efficiency of 98%. So let's start that calculation. Okay. So we have a gas turbine, and normally I try always. No, wait a minute, I do want to color. So we have a gas turbine, compressor, combustor, and turbine. Normally start numbering then 1, 2, 3, 4. So the first thing we have to know is what are the different locations, the pressure and the temperature. Well, this one we know 1.13, and we know 288 Kelvin. At 2, well, for example, assume that we have a pressure ratio of 4. So let's do that first. 4 times 103, and we don't know the temperature here. T3, we don't know. We don't. The T4, we assume P3 to be identical, so it's P2. And then we have P4 at the exit. We don't know the temperature, but we know the outlet pressure. So now we are stepping by step. We really want to have the step-by-step calculations for the TO3 and the power efficiency for the other parts. How are we going to do that? That's important to know. So if we look in the compressor diagram, and for example, we start with the pressure ratio of 4, we see that the isentropic compressor efficiency is 75%. So we do that calculation. This is one of the cases. And we also see in the same compressor diagram that the dimensionless mass flow is reduced mass flow is 342. Let's see. There we have the reduced mass 342. So we can calculate what's the reduced mass flow. So the reduced mass flow is so we have the reduced mass flow, so that's defined as m square T1 divided by P1 is 342. Well, you can derive the mass flow out of it, and that will be 20.4 kilogram per second. Because we know T1 and P1, we can very easily derive it from that. Then we have to have then we really now have to see the T2, so the compressor outlet. So we have here the compressor 288. Okay. So T2, well, we know T2 isentropic is the famous pressure ratio P2 over P1. There's a question about 342. Well, if you look on the previous slide, I think I did put it on the internet, but there's on the compressor diagram, you can see that the 342 is from the compressor diagram. So if you look like that, yeah, I share the screen. I lost my whiteboard again. But if you look for the compressor diagram, there on the dimensions mass flow, if you have the pressure ratio of 4, so you can read it in the compressor diagram that the isotropic efficiency is 75%, and the mass flow is 340. Dimensions mass flow is 342. I show that when I finish this calculation, I show it again on the compressor diagram. So you have this calculation. So you have the isentropic situation can be calculated here. So T2 isentropic is 282 times 4 times 1. So therefore we can see that the T2 isentropic is 397 Kelvin. So then we have T2 isentropic. I can share my screen like that. So in that way, if we have we have T2 isentropic is 397 Kelvin. T1 is 288 Kelvin. So delta T compressor isentropic is 397 minus 288 is 109 Kelvin. So delta compressor real is 109 divided by air isotope is 109 divided by 75%. Yep, it is. I don't know the number by head, but we can calculate that. is 145 Kelvin. The speed compressor reel. We know the CP. What do we use for the CP? I think we use a CP. I don't know, we said that should be specified, but it's not specified here explicitly. So delta H real is CP times delta T real. Well, I don't see CP specified, but assume CP then to be 1.1 times 145 Kelvin. And you know that the work is mass flow times delta H is 20.4, I think. 20.4 it was, yeah, times 1.1 times 145. And that should end up, well, you see the answer in the slide, 251 kilowatt. So this, the power consumed by the compressor is 3251 kilowatt. I will share my other screen again. So you can see it. Wait a minute, zoom. Yes. So the first question was about how do we get to the 342? Well, if you read in the compressor diagram, we have a pressure ratio of 4. So you can see we enter here with an efficiency of 75% and with a reduced mass flow of 342. So that's how we read it. We start with this situation. Then the other calculation we just solve here. So I should work them out here, and you see there's the same results. We can do the same for the turbine. So if you look back to the turbine, there also for the pressure ratio 4, and actually that's I also showed it in the class on compressor and turbo diagram. The turbo diagram is also rotated 90 degrees. I don't know exactly, probably mostly to do with easy reading, but here you have the pressure ratio of 4. And then you see there's a dimensionless mass flow at the end turbine, so at location 3. I think it's 140. And the efficiency is, it's not mentioned here, but it's 97. I think that's mentioned somewhere else. It's 87%. Well, you know that the mass flow to the turbine equals the mass flow to the compressors, 20.4 kilogram per second. And this is an important trick I like to show with you, is really how this is really the matching of the turbine and the compressor. And I worked it out here. We can see it here. If you look at the square root of TO3, so it's the inlet of the turbine divided by TO1, that's the inlet of the compressor, because those inlet values are used for the dimension or for the reduced mass flow. You can work it out a little bit. So actually, if you write this like mass flow TO3 divided by PO3, mass flow TO1 divided by PO1, well, we know the mass flow are equals. So this is actually, this one's exactly the same as here on the left side. We know this one, we read that from the turbine diagram is 139 here. Sorry, we read this from the reduced mass flow from the inlet of the compressor is 342. And if you divide it, multiply that with the pressure ratio, you come off the square root of this, and you finally end up with the real TO2. So this is important to know. Actually, if you look like this, so the combination of all these parameters really determine at what fire temperature, turbine inlet temperature you're running. So it's important to know. There's a question, these diagrams are for a specific value reduced speed, right? Yeah, that's correct. It's a single line. If you saw those compressor diagrams from some minutes ago, we have different lines. This is just one of those lines in those one specific speed. Yeah. So assume to be constant specific speed. So for example, if you run at a constant speed, for example, for compressor, for generator drive, you normally run with a constant speed. Yeah, that's true. It's a question from the chat. So this is in this case, you can very easily calculate the inlet temperature of the turbine related to the inlet temperature of the compressor Yeah. So they all relate to link together with this equation. So that's make really the compressor is really linked to the turbine performance. Now do the turbine calculation, and actually it's more or less exactly the same like I did before. I can do it a little bit here again, but wait a minute. Share screen, whiteboard. So the turbine again, then we go from 3 to 4. Now we calculated, of course, the inlet of the turbine. So at the inlet of the turbine, we calculate that to be 761 Kelvin. Now the pressure ratio is 4. So that is P3 divided by P4. And if you work that out in this case, then you can see that if you have, so you have T4 isentropic is T3 times P4 divided by P3, comma minus 1 over comma is T3 1 over 4 comma minus comma. That is, so that will be is 569 Kelvin. So then you know T, so delta T isentropic is T3 minus T4 isentropic is 2828 Kelvin. So delta T turbine real is, and it's at the isentropic turbine times T3 minus times T4 isentropic, and you can calculate that back. And if you can tell you that I don't know exactly what comes out here, so that's the 87% times 208. Wait a minute, we calculate that. It's 181 Kelvin. And then we can calculate the work again. Work as mass Cp delta T. And this comes to 472 kilowatt if you fill this in. So it look like a simple, so we have here. We have here a turbine that delivers 472 kilowatt. And we have a compressor that consumes 3251 kilowatt. So the net is at the mechanical times V turbine minus V compressor. We know that the mechanical efficiency is 98%, so that's really if you have to generate it right. So actually, so you see here that's about 821 kilowatt is available. If you so about 3,500 kilowatt. 3,000. This part is consumed. This part of the power that's generated by the turbine is used to drive the compressor. And for the remainder part, you about efficiency at 0.98%. So then you can come to this one. And then so the net power, if you work it out, then I would really I think that comes up with, we'll check that sum again. It's 804 kilowatt, 805 kilowatt. So this is really the calculation of such a system. So there you see the balance between the heat consumed by the compressor and the heat delivered by the turbine. Then, of course, we have the fuel in between. So we have 1, 2, 3, 4. Now we know this is 761 Kelvin. We know the outlet of the compressor was, I don't know, we have it back again, but that was, did we write it down somewhere? I don't know anymore. Okay, I didn't have it in mind, but we can have the Q combustor is mass CP33 minus T2. That way you can calculate also the heat that's coming into the combustor. Well, if you do that, all that calculations, and we now did it for one pressure ratio, but you can do it for the other pressure ratios. I will show it on the slides again. Wait a minute. So. So this is just the calculation for the turbine we did. So the same we see here. Same numbers. Well, then we have the netto. So they have the W shaft. So the work from the shaft is add the mechanical times W netto. Well, we can calculate the fuel input. That's the heat balance over the combustor. And then you can have the efficiency. So if you look at like this, you see that you can increase the turbine inlet temperature, and you can plot in a different way. And you can see this, the shaft power is increasing, and you see the efficiency is also increasing till about, well, 22%, something like that. So there's really a simple single shaft calculations, and I think, well, it will be one of the questions on your exam will be something comparable to this. So in the example exam, there are also kind of these calculations, but really practice them from your sample exam, this kind of calculations. Are there questions related to this task? Now then we go to the next one. Well, we see that if you put also on the compression map, you see the different points are plotted here on the compression map, the different turbine inlet temperatures. And what you see here, and it's quite interesting, that you creep to higher pressure ratios along pressure map. So you have the same mass flow, you have the same compressor, but you creep to higher temperatures and to increase pressure ratio. And this the problem if you had to close this high pressure ratio. Does anybody what's the challenge with this? If you go like this, if you look at for the compressor map, does anyone have an idea what's the Does anybody what the challenge is if you increase, if you have this trajectory on the question mark, stall and surge? Yeah, that's a good question answer. Yeah, you've gone close to the stall and to the surge line, as you see in the question mark. Jonas, how to compensate for ambient temperature? Yes, well, actually, well, we now did it for one situation. In reality, you see that this mass flow, first the correction is via this dimensionless mass flow. So you already see that if you have another dimension mass flow, you will also be in another location of the compressor map. So that's the first correction. In reality, you will also see that the performance of a compressor depends a little bit on the ambient temperature. So this, then you, of course, actually, if you look like, if you have the neat story, actually, if you look like if you look like the compressor map we just saw, so the real compressor map for different lines with the different lines of constant dimensional speed, actually for all ambient temperature, because dimensional speed is divided as the rotation speed divided by the square root of the temperature, then you see here for all these lines, they are all linked to a different inlet temperature. So actually, if you have a slightly different inlet temperature, actually you should work on a little different compressor map. That is the theoretical story, and there you will have a little bit compressor curve. In reality, if you look like gas turbine performance, single shaft gas turbine performance, you have all kind of correction curves for inlet temperature to correct your power and efficiency to the ambient temperature. But the real story is actually you run a little bit different on the compressor map, and there's a little bit different on the turbine map, but there are more inputs to ambient temperature. Maybe a little bit more heat loss, things like that, that's not included in it. But well, in these simple calculations, we don't correct for the ambient temperature, but in reality, you should do, of course. Okay, let's finish it till now. I'll give you 5 minutes break. Yeah, 5 minutes break, and then we continue with the twin spool gas generation and free turbine. Okay, I had 2 questions here in the chat. Is there also a mechanical limit to the max compressor speed that's only limited by choking? No. I think at the end of this class we will discuss also limit of stresses and things like that. And then the optimum compressor speed is actually compressor normally you run at transonic speed, so Mach 0.7, 0.8, then you have the optimal performance, and then otherwise you get choking. So they really have a limited area of operation, otherwise you enter search and stall limited like that. But yeah, you have all kinds of things like I said, stall, like if you start up a gas turbine and a compressor, you have all kinds of different rotational speeds where you go to stall. It's also the stress in the compressor. So the compressor has a large number of limits. So there's a really, the compressor has quite a limited range of operation. So you should be well aware if you operate a compressor that stay in with those operational limits. Then the next question is from Dhruv about the TU studies about uploading of the assignments. Well, if I don't know, I think the first two assignments have been handed in. They have to be handed in by René Pesnik. I think, well, please contact him. If you didn't put it on Brightspace but emailed him, I think it will not really be an issue. But we have to make it possible for us to keep the administration going. So it might get lost that he doesn't see it on Brightspace and said, hey, where's your assignment? And maybe don't get it in his mail. So if you have a question about this, please send an email to René Pesnik and please also submit it via the Brightspace. I think that would be the most needed way to do that. Okay. Let's continue. So now we only had a single shaft gas turbine where we see that the turbine part, so in this case it's the between 3 and 4, generates more power than we consume by the compressor. So then we have some power available. In this case, this was a single shaft. If you look at the twin shaft, it's a little bit different configuration. And these twin spools we come back into later in the applications. Is used in a number of applications, especially in airspace applications. And important to know about this twin spool is that you have the first turbine and compressor, they are called a gas generator. So actually they just generate gas to drive the power turbine. That's their main role, to drive the power turbine. And to the power turbine, you have a load. You can either have a compressor, a pump, a fan for a helicopter or for an airplane. So this is really, this power turbine drives some useful load, and this gas generator is to deliver the right gas at the right temperature and pressure of at 0.4. So that's important here. So important aspects of the gas generator or about such a twin shaft turbine is this turbine, actually this compressor turbine is only used to drive the compressor. So there's a mass balance or an energy balance between this turbine and this compressor. The other matching parameters, if we assume a small fuel flow, is that we have constant mass flow to the system. Make also life easy. And like I said, was actually this same equation we discussed just before the break for the single shaft turbine. You can relate the turbine inlet temperature and the inlet temperature to each other with this equation and the pressure ratio. So this is important here. And important here is actually, if you look, we come back to it later, but the big advantage of this system is that it can run freely at a different speed than the power turbine. So you can deliver the right amount of mass flow. And as you saw in the compression diagram, it's a kind, the mass flow really gives a kind of steep line. And if you have a single shaft, you have only limited mass flow you can use. But by running this at other rotational speed, you can suck in more or less mass depending on the request from the power turbine. So if you have the twin shaft calculation, well, we just had the single shaft calculation. If you go to the twin shaft, well, I worked them all out here, and we don't go into detail, but you can find out that you will have about 17 unknowns. And then if you work all the equations, you will have 16 equations. So you have one, so like I said, well, because for the bottom, the zero energy balance of the gas generator, so the balance between the turbine and the compressor of the gas generator. you know the power delivered by the power turbine. We know the energy and pressure balance over the combustor, the atmospheric conditions, the energy balance of the turbines and the pressure balance of the turbines, turbine charge, compressor charge. Well, if you all sum it up together, you come to 16 parameters and 17 unknowns. So you have 1 degree of freedom. And we excluded here the inlet guide frame. There's an extra degree of freedom. You can really, this actually included the part of the compressor chart partly. But if you don't have the inlet guide frames, you have 17 equations, 16 unknowns. So in normal situations, that will be much too complicated to solve that by hand. So we make in our exam questions, we might either discuss only the gas generator or either only the compressor turbine or only the power turbine, but we won't ask you to do a complete energy and mass balance of a total twin shaft. We can ask that, of course, for single shaft. That's more easy. Well, there are some simplifications possible, and to get some idea, I think that's really to better understand, we do it now to better understand the performance of such a turbine. And we can do that actually if you look at the inlet and outlet of the gas generator. So we define a dimensionless mass flow at the outlet of the gas generator, so the outlet of the turbine. So that's in this situation, this location. So the turbine of the gas generator is indicated by 4. And actually the compressor diagram, the turbine diagram is defined by the dimensions mass flow at the inlet of the gas generator. Well, we can rewrite this. So if you write this and you introduce these parameters, so this is just mathematics that you can write it this. Well, so we know this one from the turbine chart. And if you know these parameters, we can also have the dimensions mass flow, the reduced mass flow at the exit of the turbine. Well, if you look like this situation, you can work a little bit out. And if you assume, you can also rewrite this like this. And we know this equation, we derived that in the beginning. That's this equation of the efficiency of turbine. So if you now assume a constant efficiency turbine, you can write this, and you have this one, like this efficiency, the only efficiency of the turbine and TO3. So you can write everything as function of TO3 and the pressure ratio, and that's important to do. So if we do it like this, and I can explain it a little bit here. So this is normally, if you like the turbine diagram, you normally have a picture like this. So where you have the choke flow at the inlet of the turbine, independent of the pressure ratio, you have a constant reduced mass flow at the inlet of the turbine. So you don't have a constant mass flow, but you can't have constant reduced mass flow at the inlet of the turbine because of the scaling with the Mach number. Because of choke flow at the inlet of the turbine. That is this one. Well, based on this equation, we just derived with the different steps. You can also calculate the outlet curve of the gas generator turbine. So this is the outlet curve of the gas generator turbine. If we go 2 steps back, the outlet curve of the gas generator turbine is here. That's again the inlet curve of the power turbine. We go like this. So it's the outlet curve of the gas generator turbine. And if you then plot right from it the turbine curve from the power turbine, and I think this is one of the reasons why they shifted the X and Y in the turbine versus the compressor. If you plot in this way, so the pressure ratio versus the reduced mass flow, you see that here, in this situation, if you choke head, so this value here, that's the outlet of the power outlet of the gas generator turbine, should be equal to here the inlet of the power turbine. And that makes very interesting that this is the maximum, because you have the choke inlet, this is the maximum reduced mass flow at the inlet of the power turbine and therefore at the outlet of the gas generator turbine. So you add on this location, independent where you are here on the power turbine curve, you always end here with this reduced mass flow at the outlet of the gas generator turbine. And well, we know this is one-to-one related to the inlet of the gas generator turbine. So we know here we are here on the turbine curve for the gas generator turbine. So very important to note that the choking of the power turbine really determines where are you running with your gas generator turbine. And this is the maximum pressure ratio. So you can't have any higher pressure ratio on this over the gas generator turbine. So always when you're running here on the power turbine, you always have at the same pressure ratio of the gas generator turbine. That makes life a little bit easier. And if you, for example, would here, if you would be not on a choke area of the power generator turbine, so you would have a low pressure ratio or low load, you will always have a lower pressure ratio of the gas generator turbine. So if you do it a little bit like this, so you can work it all out together. All the other parameters you can express a little bit in each other. So it's the PO3 of PO4, so it's constant over the by choke turbine. So that's the pressure ratio over the pressure ratio over the turbine from the gas generator. We can work it out. Well, the pressure of the combustor is constant. We know this one. We can also work PO2 over PO1 out. If you look like here, so the pressure ratio, so the PO3 of PO4, so that is, like I said, that is the pressure ratio of the gas generator at the turbine. That stays constant. You see the compressor turbine, the compressor increases, and also the power turbine increases. So it's important to know here. And really and therefore actually that also determines finally, if you look at this complex system of the compressor, the compressor turbine and the power turbine, the swallowing capacity, so actually that's where the choke flow of the power turbine really dictates where the system is running. And that is very important to know that swallowing capacity of the inlet of the turbine is really, if you do make a simple gas turbine model, that is one of the most important parameters, together with the compressor curve, where you run on the compressor curve. That's really important. Well, if you do it like this, but also with these simplifications we do, I don't work it out in detail, but you can have the choke turbine, then we have the choke power turbine, you have the compressor turbine. Well, if you do all these calculations, also with these simple calculations, well, if you're very fancy, maybe you can translate it once a time in a computer program, but then you can really calculate the efficiency of such a system, where you make all the sums with the constant efficiency and constant turbine efficiency and things like that. So over with these simplifications, you enter with this complex set of equations to solve for a twin shaft turbine. But the main message I want you to give is it's really determined by the swallowing capacity of power turbine where you run in the cycle. The same we have here. For example, if you look, for example, worked out for such a simple model, for example, these are the same equations you saw here. These are the PO3 and PO4. So these are the temperatures. So the TO4, so the TO3, that's the inlet of the compressor turbine, the inlet of the power turbine, and then you have, so these are the situations. And different loads, you see how they vary. The big advantage, actually, if you look for part load performance, is for a multi-shaft turbine, is that you have quite a variation in the mass flow. Where single shaft, you run one rotational speed, and especially when you are at the stone wall, like I just saw the compressor curve, at the right side of those compressor diagrams, where you normally are with a high efficiency gas turbine, you more or less have a constant mass flow, unless you lose ISDVs. The big advantage of such a multi-shaft turbine is that you can vary the mass flow the mass flow of air depending on the power you run. Well, these are complex calculations. So we have complex user software, so you can DSP, so developed by NLR and TU Delft. there is a class, I think it's updated now, so I don't know it's the real right class, but aerospace engineering, they have an interesting class, so that's given by Wilfried Visser and Piero Colonna, and that is on simulation of thermodynamic systems. If you're ready, you can look it for yourself in the aerospace study guide. That's a good class if you really want to know more details about simulation of those complex systems. And well, there are all kinds of methods. So actually, the Thermoflex software is also kind of simulation we use for there, but all kind of complex software to solve these issues. Yeah, so this is what I just actually want to tell you. That's the advantage if you have multi-shaft turbine. If you operate the twin spool, you operate according to this line. So you're here, and also it's also these are all bubbles of highest efficiency of the compressor curve. And actually, with operating on this line, you're always more or less to the maximum or the best efficiency on the compressor curve. If you look on a single shaft, you run on this line we just saw, and you have quite a variation in compressor efficiency, and you also have very limited variation in the mass flow. So especially at part of operation, you more or less have the same constant mass flow. You can change a little bit ITVs, but it's one of the main disadvantages of a single shaft versus multi-shaft is the constant mass flow. We have a very mass flow and also more and high efficiency in this situation. So that's one of the advantages of a dual shaft versus single shaft. Another advantage we can derive here, well, you can find it out. But if you look at the single shaft, so this x-axis plotted is plotted the speed and the y-axis plotted the torque. If you have a single shaft, in this case, you don't have any mass flow at zero speed because you're not rotational. You only get mass flow and only get pressure built up if you rotate speed. So if you have this situation for a single shaft, this is the maximum torque it can deliver. But if you look at a multi-shaft like this one, because the power turbine can run independently of the compressor of the gas generator. So this is the rotational speed of the power turbine, but the compressor turbine can run at a much higher speed, so can suck in a lot of air, and still it can also deliver quite some torque at very low rotational speeds for the power turbine. And because that is decoupled, you really see you can match it here. And if you have other speed, it automatically finds a sweet location to operate. And there, of course, you have that split between the gas generator and the power turbine. You can really see that for non-constant speed drive, for example, fans or in aero engines, pump drive, you normally lose those twin shafts. If you constant speed drive, for example, for generator shaft drive, to supply the electrical kit, you can apply both. For the big ones, normally heavy duty, so the single shaft are more applicable, but you can also use with a dual shaft in that. So there, it's some possibilities. And the big advantage of a multi-shaft with constant speed is that you can still have a constant speed for the power turbine, but varying speed for the compressor turbine, and that way you can have a constant fluctuating mass flow, varying the mass flow over the power. There you can achieve a little bit higher part of the efficiencies with a twin shaft normally than with a single shaft. But if you really want to have the torque, you really need twin shaft to do that. Now, make some calculations. You have to show that because these are the complex calculations I just showed you, but we have some ideas. Normally, you have kind of ISA tables where the typical numbers are put in here. And what you see, if you normally, this typical number for this is a business jet airplane, but typically an airplane, the power required for takeoff is about 4 times higher than during cruise. So if we look a little bit deeper into the system, how would you operate such a system on sea level and on cruise level? So you can see here, so there's 288 Ks, it sucks in the air, compresses it to 20 bar, then it heats up, expands in the gas generator, and here the outlet, 20 megawatts. and the same on the cruise. There are a number of differences in the situation. And maybe it's already a bit linked to the next case. But if you look like this, so this situation is sea levels take off, so it's a maximum power level, and this is cruise long tail, long run. Does anybody see something very special or attractive between those two situations? So the cruise situation, the sea level situations. So please answer your question in the chat. What's the delta P over the, I think it's a dimensionless. I don't know if it's an error mistake, but normally it's the same percentage. So it should be this percentage. I think that maybe there might be some numerous mistakes. So normally you assume 2%, 3%, or 5% pressure loss. I think there's a little bit more than that. But that's not the main difference. There might be a small mistake between the pressure double cost combustor between sea level and cruise. Yeah, that's true. I fully agree. A 3-bar pressure loss of the combustor is not good at sea level, but it's not the main issue. That's a good observation. This is too high. So I will check that. Does anybody see something between the cruise at high level at 30,000 feet, 10,000 kilometers, 10 kilometers, and sea level operation of the gas turbine? Air intake is high, yeah, okay, yeah, that's true, yeah. Yeah, but yeah, okay, but that's just because you probably also need more air. Turbine outlet is in vacuum, yeah, that's not, yeah, that's a vacuum. It's because you are here at a higher atmosphere, so you have a lower ambient pressure at 10,000 or 20,000 feet, 10 kilometers. Does anybody see something else different? Yeah, burning temperature is higher temperature delta T. I don't understand that. Can you please explain it a little bit better? What you mean by that? Yeah, much lower pressure side of turbine. Yeah. The delta T of the turbine is higher. Yeah, it's a little bit higher, but it's mainly linked to the pressure ratio. Now, if you really see what's important, and maybe that's a little bit linked to the next question, if you look like material properties, so if you look like the turbine inlet, what do we see in difference in the turbine inlet? That's really the life limiting part of a gas turbine. What do we see there in difference between the sea level situation and the cruise level situation? Yeah, the 600 K difference in temperature, inlet temperature is far higher. And why is it allowed to be that high? So is there an optimum? I don't think this is not a real situation, but a realistic case. But is that, yeah, I think that's why it is short term. So the sea level, this high temperature only occurs during takeoff, so very short periods. And you will see next class that for these materials, they're very sensitive for high temperatures, for oxidation, creep, and all kinds of fatigue. They're all limited to this temperature. But if this temperature only is a short period, you only have a little bit life consumption. And if you have a reasonable temperature here during the long period you're running at cruise, this will mean that this temperature, this material will stay for a long period. So that is really a balance also if you look at these aero engines, but also for gas turbine engine power generations, how long is the period you want to run at high temperatures. In this case, you can run, yeah, this 1200K, well, it's not a real problem, but 1864K is quite challenging for materials. So in this way, they found a balance, and actually it's a natural balance because of the other atmospheric conditions. Therefore, it's, yeah, you can use with the same engine, because that's the advantage. You don't have a separate engine for takeoff and cruise. You can, with the same engine, you only have well, you have quite a high life consumption during takeoff, but it's a short period, and a low life consumption during cruise, but that's a long period. So there's a good balance. But it's important to know. It's also linked to the next class. This is really important. This inlet temperature is really an important parameter that determines the performance of your cycle and also determines the life of your gas turbine. Well, I can plot on the compressor diagram, I see sea level a little bit, but it's closer to the search slot, so the quite convenient curve now running on the sea level case. And you can also see the power of the turbine. And what you also see here is that just the cruise temperature, but this is the sea level temperature and the pressure ratio, and you also see here the efficiency. So it's the sea level efficiency and the cruise efficiency is here plotted here. Here. So it's also a little bit higher. So it is also advanced because then you this 35%. Actually, because you're running a long time at this period, so you want to have a high efficiency than a situation where you run a short period at a high temperature. Okay, the last I want to discuss today, it's about dimensions and a little bit. Well, we saw in the beginning the question we had from one of the students about by what is the operation of a compressor limited. Now, if you do it like this and make it a little bit simple, so if you really see the mass flow of a turbine is something like the density times dimension times RPM. And the same is to the pressure height. Well, I think I can ask you the question, but I can work it out easily. I think so. We do it in the wait a minute. So we have the flow. So that is something like U times the area. So U scales with, and then we do it also with the mass flow. Then we do the density. U scales with the rotation speed times the diameter. The area scales with diameter squared. So if we all combine this together, this scales with flow, scales with rho, and d3. So if your pressure, well, that scales with rho u square. So if you do it like that, that scales with the rho n square d square. Power scales with is Q volume flow times delta P. So this is volume flow is n delta P as rho n square d square. So that scales with rho d to the power 5. This is important, simple calculations how they scale with each other. So let's work it out here. We work it out here. D5 square n square t square. Then we have the compressible flow limit. Well, we have the rotational Mach number. Well, actually, we worked it also out together before. So then is the, of course, you then have sorry, then you have the diameter, just the velocity, the u, and so that the velocity is n times d divided by the speed of sound, and it is square root of the temperature. And then we have the mechanical stress, because also one of the limits, we work them out here. So rotational Mach number, d squared with d n, and we have the mechanical stress. Well, you see actually the mechanical stress is really related to the rotational situation, so the centrifugal forces. Well, if you work out these centrifugal forces, you can see that the stresses rotate with d square n square. So if you have the same diameter and you rotate twice as fast, twice as high speed, your stresses go 4 times as high. Well, if you look at the same power rating, so we have the same one here in the beginning, so D5 and 3, assume that will be the same, and you vary the diameter, and then you get actually the relative RPM. So then you scale with this one. So with the smaller diameter, you need a higher RPM, like this. Important here is that the relative weight, that scales also with d to the power 3. You really see that it increased here significantly. So therefore, actually, if you look at aero engines, they normally work at a lower diameter to save on weight. If you have a big gas turbine on the ground, yeah, you can sit here and you can have the biggest diameter possible. So that's actually what we're running with heavy duty here, the bigger diameter possible. That's only limited. That's really only limited by the rotational Mach number, so that you have a Mach number of 0.8 at the outside of the inlet compressor with the highest the diameter. So here you are with the heavy duty somewhere, and here you are somewhere with your aero engines. Because what you also see is the relative stress, because of this increase in rotation speed, also increased significantly. So then you really want to be something here. So it's really a balance between where you sit on the diameter, rotation speed. So that also determines the design of your gas turbine you use. So what are we going to the summary of today? So the single shaft, we did some calculation for that, is normally for constant speed drive, and 9 of the 10 cases that is for generator drive connected to the grid. Well, we saw the multi-shaft gas turbines are well suited for optimum torque generation. And important, actually, the swallowing capacity of the power turbine, together with actually the compressor maps, everything really dictates the cycle parameters. We saw that in the single shaft where we did the calculation, but also saw the examples for the multi-shaft. And there's also one degree of freedom. We saw it in the single shaft. If you do complex calculations, you also see it in the multi-shaft. There's 1 degree of freedom. So for example, the turbine inlet temperature, are they all linked together? So that's only the degree of freedom. Only in the case of a variable state of IGV, you have an extra degree of freedom. So you can have that one. So normally, if normal operational wide and also you control a gas turbine, you should be aware of that. These are the degrees of freedom. You only can turn R1 or 2 per buttons you can run on. Okay, this is the class for today. So next week, coming Friday, you will have the class from Piero Popovic. And from then on, yeah, she will have 2 classes, and then I will take over again. Are there any questions? Okay, I didn't get why the torque decreases with the rotational speed. Is rotation speed? I come back to that. I don't have a simple answer to that. I come back to that, Matteo. So that's not an easy answer. I come back to maybe it was. I have to check it if it has been evaluated at constant speed, because then it's logical. Because maybe constant speed or constant power, you will have a decreasing torque at constant speed. But I will check that. I will check that, Matteo. Yeah. More questions? Okay, then I'll leave it for here now. If you have any questions, please email me, or I will see you in 1.5 weeks from now. So next week, Friday the 18th. And have a nice evening, and see you. Goodbye.
Okay, thank you. Bye.
Bye-bye.